SwayamPrabha. Digital India. Educated India.
So now we are going to start our next module, module number 4, that's called as simplified stamping process or simplified stamping analysis, we can say. So in this particular module which we are going to complete now in this session itself, so we will see how to do a simplified analysis of a stamping process. Certain things which we have already studied and certain things will be new to us in this particular chapter, and already whatever we have studied we will try to put it for the simple simplified stamping analysis. Okay, so what are those assumptions? Okay, how we are going to apply whatever we discussed before for this kind of stamping process is what something we need to know, so that complexity involved in stamping analysis can be reduced. Okay, so though it may not be fully accurate, we will see that, but it will give you a very good idea of what is going to happen in the sheet during stamping process. So stamping process, what do you mean by stamping process? So stamping process means, for instance, it could be any sheet deformation process. It could be any sheet deformation process. Okay, generally it's of industry component level. Okay, so suppose you want to make some component, for example, your front bumper, rocket panel, tunnel, okay, B pillar inner, okay, roof rail inner, something is called as subplate. These are all actually stamped products. Stamped product means actually from industry point of view, okay, you can make that component by sheet forming. Okay, generally they are of shallow parts, which is required depending on the situation. Okay. So it is stamping is a very conventional process used in industries to make many such components, okay, which cannot be made by simple bending or folding process. Okay, so which cannot be made by simple folding or bending process. And this stamping process will involve mostly stretching type of deformation. Okay, that's what is indicated. They used to form shallow parts in the press by stretching the sheet over a shaped punch or die. There can be other tools also to create that shape. Okay, so and like your sheet forming process can be divided into two important categories depending on the temperature, working temperature. Here also you can call it as hot stamping and cold stamping process. Hot stamping done at elevated temperature, cold stamping done at room temperature, depends on the material. Okay, some examples are given here. Cold stamping is used typically for lightweight materials like aluminum alloys. Hot stamping is generally used for high strength steels, HSS or UHSS, ultra high strength steel sheets. Okay, so many examples are given here. This kind of components can be made by using let us say different hot stamped automotive parts are shown here. Similarly, cold stamping is also possible. So this will give you a fair idea of where we stand when you discuss about stamping process. So this is the context. Okay, so just to tell very basic tools required for stamping process, which is already known to us. These are all conventional tools available to us, but then it's more of a intricate shape that is required here. You can see that this diagram A, B and C, which are taken from this particular book. So you will see that it has got a punch, okay, and it has got a blank or a sheet, okay, and you will see that there is a blank holder, okay, and there is a die kept here, and there is a draw bead, okay, on these locations. It's a sectional view. It's a sectional view, you can say. They all are there. Okay, so now punch is not touching the sheet here. Okay, there is a gap. Okay, so now punch is going to move down and is actually stretching the sheet, okay, on its surface. So now you keep pushing down, some shape will be formed, and if you want to have a counter punch, counter punch can also be pushed from the bottom side, okay, and it can deform the sheet in this region, okay, so that if you want to make any re-entrant shape, that can be made. Okay, re-entrant shape means you can see that the sheet is deforming like this, and then there is an inward movement of the sheet, and then it is coming down and it goes undeformed. This kind of re-entrant shapes can be made by with the help of a counter punch. Okay, so punch, you have a blank holder, you have draw bead, and then you have counter punch, and of course you need a die. Okay, all together is going to give you this particular shape. Okay, but it is not mandatory that you need to have a die, because you can make a unshaped component. Unshaped component means the component shape is derived by how much you deform. Okay, so in this case you can see counter punch can be seen in the form of a die, which is going to give you some shape at one particular location. Okay, these are all certain important tools. These tools are known to us. Okay, and I hope you understand the meaning of blank holder. Blank holder is to hold the sheet, which means that this can be done in a double stage stamping process. Double stage means two stages. One is, first of all, this blank holder will come and hold the sheet in this location. Okay, in this location it's going to hold the sheet, and then your punch will come and then it will deform the sheet, and the punch will keep on deforming until that the last phase of the deformation you have to hold the sheet. Okay, blank holder has to hold the sheet. Otherwise, if you don't provide appropriate blank holding force, there will be lot of wrinkling that will happen in the flange of the sheet. Flange of the sheet is this. Okay, so it's a double stage stamping process. So blank holder has to be used to hold the sheet. That is number one. It will come separately, and then punch will come down to deform the sheet in this fashion. Okay, so now if you want to analyze this particular process and then calculate certain important quality, okay, quality of the sheet at different locations. Okay, quality, when I say how much strain it can withstand at one particular location, how much thickness it can withstand at one particular location. Okay, and then how much is the tension, T1, T2, sigma 1, sigma 2, principal stresses. So all those things, what will be beta, alpha at different location. So all those things can be calculated from whatever we have studied before. How we are going to put that into this situation is what we are going to see now. So now we are going to consider something called as a two-dimensional stamping model. Two-dimensional stamping model, and a typical schematic is shown in this particular figure. Okay, schematic of a 2D stamping process is shown here. Okay, there are a lot of nomenclature one has to indicate with respect to this figure, and I have noted down that. Okay, so we will go one by one. So you will see that, so this black color one is the sheet. Okay, this black color one is the sheet. It has got O, A, B, C, D, and then this particular portion is actually zoomed in here. Okay, A, B, C, D, then E, then F, and at the end you have G. Okay, so O, A, B, C, D, E, F, G actually covers one half of the sheet metal component or stamped component. Okay, so now here you can see that punch is actually deforming the sheet. Okay, punch is actually deforming the sheet. Okay, and hence you are going to call this height as penetration height or draw depth, something like that you can call. So you can call it as punch penetration. How much height it has deformed the sheet. Okay, so with respect to punch, we are going to call this A as punch semi width. Okay, punch semi width. So this from center axis to this particular portion is actually your punch, one half of punch. So we call it as punch semi width. Width of punch width, but it is a semi width, A. And then you are going to have this B. B is called as blank semi width. Blank means sheet. Sheet semi width. One half of the width you can say. This is B from this axis to this end. This is B. C is a side clearance. C is the side clearance between your punch and your blank holder, or punch and the die you can say. So here you have to be a little bit careful in deciding what is C. As we discussed before, there should be appropriate clearance between the clearance defined by C. Otherwise, what will happen here is lesser the clearance, that means clearance is lesser than the sheet thickness, for example, then you are going to have ironing. We will see that briefly later on. That should not happen. Larger clearance will also create other defects in the material. Okay, so we need to have appropriate clearance that we discussed in the first section. So then we have something called as E. Okay, A, B, C. Then we are going to call this as E. This E is this particular region. We call that as a land width. Okay, this basically this E is a region where you don't have any compression force or blank holding force that's going to act here. Okay, nothing is acting here. Okay, when compared to F. So when you go to F, that is where you are going to have clamping. Okay, F is nothing but width of a frictional clamping. Okay, that is where you can imagine that there is a draw bead, okay, and it is located here, and that's going to give you some clamping force, restraining force to the sheet. Okay, or you can have you can imagine that there could be a force, equivalent force, whatever draw bead force is given, an equivalent force can be given at this location, which can restrict the movement of sheet. Okay, that all are going to happen at this F. Okay, in this width. H is already informed to you, and T is a blank thickness. Okay, at any location you can pick up. Okay, T, and there are three radius: RF, RP, and RD. Okay, so RD is a die corner radius, RP is a punch corner radius, RF we are going to call that as a face radius. There is a small radius, okay, given to the punch. Okay, there is a small radius given to the punch. Okay, so it is a little shallow in nature, you can imagine. So that is RF. And there are different zones one can define. Okay, one is OB, material in contact with the punch. From O to B, you have contact with the punch. And from B to C, it's unsupported region, that is nothing but your side wall. Like in deep drawing, we say cup wall, no? So here BC is unsupported region. Okay, that is your cup wall between your die and the end of punch. Okay, and CD is actually sheet in contact with the die corner radius. So wherever you have contact in this RD, that is your CD. And your DE is basically sheet on the die land without contact pressure. Okay, so this land width we said, no, in that location whatever sheet is available, you call that as DE. And EF is a region on which a blank holder force is acting, that I already indicated. You can call that as, let us say, B. Okay, and FG is the free edge of the blank. Okay, FG is a free edge on a blank. So now it's going to have, since you are going to clamp it with some blank holding force, you will see that the sheet is going to stretch, okay, on the punch surface, and you are going to make some component, and we are going to call that as a stamping operation. And this angle theta is going to be important, and this theta is actually referred with respect to this particular region between A and B. This is basically the inner angle here. Okay, and this angle is same as that of this particular angle, which is subtending with respect to your cup, your or die or your side wall. That is between basically your BC. Okay, between that is along BC. This angle, both the angles are same, theta and theta. This fellow and this fellow. And B is a blank holding force that is going to act, which is what is shown here. And you will see that this F is the punch force. F is the punch force, that has to be calculated. Okay, punch force will change with respect to H. F is going to change with respect to H. There is a typical diagram. You can draw F as with respect to H. Okay, F is going to change with respect to H. So these many details are there in this particular figure. And then what we are going to do is, we are going to do analysis on this. Okay, so now usual way, we always start with strain of an element. So what we are going to do is, assuming there is a punch, rigid punch, okay, this punch is given here with this yellow color one, and below that you are just picking up a small element in the sheet, that is this orange color one, and this is your sheet. The gray one is actually sheet, a part of sheet which is below the rigid punch, which is actually getting stretched, actually getting stamped, and there is a small element you are going to pick up. Okay, and that element strains and state of stresses are shown here. Okay, and the directions are shown here. So basically along the sheet we are going to call it as 1, perpendicular to that is 3, and perpendicular to the plane is actually 2. We are going to pick up that as 2. So perpendicular to your sheet, perpendicular to your die or the plane of the diagram is actually 2. Okay, so we are seeing an element deforming and sliding below punch face. So this could be anywhere here. You can just simply say anywhere here. Okay, in this location or in this location, anywhere here. Okay, so what we are saying is basically epsilon 1 okay, that is nothing but strain, okay, direction on the sectioning plane, okay, sectioning plane, okay. So you are going to section this entire setup, no. So on that plane you are going to have 1. So that is what is given here, and epsilon 2 is nothing but beta into epsilon 1, that is known, okay, that is perpendicular to the principal direction. That means perpendicular to the plane of this particular diagram, that we are going to call it as a plane strain, and that is going to be 0. Okay, so epsilon 2, that means along this 2 direction we are going to keep that as strain as 0, because the material is actually not constrained in that direction. Material is actually not constrained in that direction. So you can imagine that this particular section will remain the sectioning plane. You can cut that entire setup at any location, this situation will remain same. Okay, so this section is done at any location, this situation, okay, your punch, die, all this situation, your sheet situation should remain same. Okay, so which means that there is no constraint for the sheet to deform in the 2 directions. So you can call that as a perpendicular to principal direction. We are going to call this as 0. This is an important one for us. Okay, and epsilon 3, this we already derived, minus of 1 plus beta into epsilon 1, and since beta is actually 0 here, so you can put minus epsilon 1, that is because of beta is equal to 0. And we already have an assumption sigma 3 as 0. Okay, so that is what is noted down here. Okay, so you will see that sigma 1 epsilon 1 will exist, sigma 2 will be sigma 1 by 2. So if beta is equal to 0, what will be alpha? We will see epsilon 2 as 0. Okay, and you will see that sigma 3 is anyway 0. Okay, because we assume plane stress assumption here also, and epsilon 3 is already here. Okay, so this is the situation we have, and you know how to get epsilon 1 and epsilon 3. Okay, you assume that in this location a circle grid is plotted like the way we did some problem. Okay, and the circle grid will get deformed after some time until there will be different dimensions. From that you can get epsilon 1. Because of the situations, epsilon 3 is nothing but minus epsilon 1. So it becomes a simple case. Now if you want to evaluate effective strain in that particular location by assuming von Mises yield function, we already derived this. Epsilon bar is nothing but square root of 4 by 3 into 1 plus beta square. Outside is epsilon 1, and then if beta is 0, these fellows become 0. So then it will be 2 by square root of 3 into epsilon 1. So epsilon bar also can be found out at that particular location. So second important thing after strain evaluation and effective strain evaluation is the thickness. Thickness is going to be important because we do not want thickness to reduce beyond a certain limit. Okay, otherwise it will lead to instability. Right, instability like necking, fracture, which you will see in the next chapter. Okay, so thickness, how do you get thickness, the new thickness? Okay, that also can be obtained by original expression, T is equal to T naught exponential epsilon 3, okay, and beta to be equal to 0, it will be directly T naught exponential minus epsilon 1. So that also can be evaluated. Okay, so where T naught is your original thickness and epsilon 1 you know how to get it with respect to circle grid measurement. So now let us come to the state of stress. So as I already discussed with you, sigma 1 is going to be there, and sigma 2 is equal to alpha into sigma 1 as per our definition. When beta is equal to 0, alpha is going to be half, and hence sigma 2 is nothing but half into sigma 1, which is nothing but sigma 1 by 2. And sigma 3 is going to be anyway your 0. Okay. So epsilon 1, epsilon 2, epsilon 3, epsilon bar, thickness all are found out. So now we have sigma 1, sigma 2 and sigma 3 also. Okay. Now all are known at that particular element below the punch which is undergoing deformation. Okay. So now how do you get sigma bar? So for sigma bar, if you want then you need to go for effective stress relationship with effective strain. Okay, and it is given by this particular equation. Okay, sigma bar is equal to K epsilon naught plus epsilon bar power n, where epsilon naught is nothing but your pre-strain value. This we discussed in the previous section. Epsilon naught actually is called as pre-strain, and that is going to take care of the prior deformation of the sheet before it comes to the present stage. Okay, so that is why when you say this strain as 0, there is going to be some sigma bar available in the material which could be equal to your yield stress. Anyway, fine. So now if sigma bar is equal to K epsilon naught plus epsilon bar power n, okay, then what we need to do is we need to put epsilon bar in this equation. Okay, So because epsilon naught is a constant, k and n are material constants. Okay, epsilon bar is going to change, and it is going to change with respect to this particular equation which you already derived. 2 by square root of 3 into epsilon 1 I am going to put here, power n. Okay, and then sigma bar can be obtained. So if I know sigma bar, I can get sigma 1 by relationship sigma bar divided by 1 minus alpha plus alpha square from 1 minus effective stress. Alpha is equal to half if I put. So it will be 2 by square root of 3 into sigma bar. 2 by square root of 3 into sigma bar. And if sigma 1 is known to me, I can get a sigma 2, and sigma 3 is anyway not available for us here. Okay, so these all are already available for us. Only thing is, depending on the stamping process, assuming it to be plane strain and of course plane stress, sigma 3 as 0, we are going to simplify all such analysis in this way. Now, there is one important point that we are actually changed this equation sigma bar is equal to k epsilon naught plus epsilon bar power n. Now what is going to happen? So now if you want to get T1 and T2, okay, T1 and T2 were introduced in the previous section, okay, where T1 and T2 are nothing but traction force or tension, okay, like this diagram I think we discussed in the previous class. Okay, in y axis you have T1, T2, x axis let us say epsilon 1, and T1, T2 are going to vary like this, and these two are related by alpha. These two are related by alpha, right? And we said in the previous class that whenever maximum tension T1 is going to happen, okay, then that can be defined by epsilon 1 star. Okay, whenever epsilon 1 becomes epsilon 1 star, okay, then we say maximum tension is going to happen. And I think in the previous section we derived epsilon 1 star is nothing but I think n. Okay, by assuming sigma bar is equal to k epsilon bar power n, I think. Okay, so you can refresh that. So epsilon 1 star is equal to n we discussed, I think. Okay, anyway, or I think we discussed n by 1 plus beta maybe. Okay, so maybe we will check it. So that you can refresh it. So epsilon 1 star will be equal to one particular value, then maximum tension will happen. Now but T1 can be found out as nothing but sigma 1 into T. Where sigma 1 is nothing but sigma bar divided by square root of 1 minus alpha plus alpha square, and sigma bar is nothing but k into epsilon naught plus epsilon bar power n, and epsilon bar is nothing but your effective strain, this fellow power n, like T naught exponential minus epsilon 1, this we already derived. Okay, so now when we say beta is equal to 0 and alpha is equal to half, this equation can be reduced further, which can be written as if you say alpha is equal to 1 by 2, then it will be 2 by square root of 3, okay, into k will remain as it is, T naught will come here, into epsilon naught plus this entire thing will become, if you put beta is equal to 0, 2 by square root of 3 into epsilon 1, which you already derived, power n exponential minus epsilon 1, and in this way you can get T1, and T2 would be T1 by 1 by 2 because alpha is equal to half, right? So what are the variables here? You can see T naught is the original thickness, K is the strength coefficient, you know how to get it, N is a strain hardening exponent which will be given to you, pre-strain is a very small value, let us say 0.005 or 0.008. So all are known to us, only difference is there is going to be epsilon 1 which is a variable. Okay, so now what we are going to do? So we are going to obtain epsilon 1 star, for this equation. Okay, the main difference is there is epsilon naught here. In the previous section we derived an equation for this, similar equation for this equation, and here we are going to introduce pre-strain. Then if you say by differentiating T1 we obtain maximum tension at a strain, epsilon 1 star is equal to n minus root 3 by 2 into epsilon naught. N minus root 3 by 2 into epsilon naught. If there is no pre-strain, then this factor will go off. That's what I was telling you, epsilon 1 star will be equal to your n. So when you put beta is equal to 0 here, so you will see that epsilon 1 star will be equal to n. Both will remain same. Okay. So the only addition we have is minus root 3 by 2 into epsilon naught. That comes because we are going to include pre-strain into this particular strain hardening law. Okay. So and we are going to say that this star generally refers to a limit strain value. Okay. And epsilon 1 star is known to you. Epsilon 2 star can be obtained by beta into epsilon 1 star, providing your beta is going to remain same, okay, when you reach this particular stage of deformation, which may not be true also. Okay. So but assuming that your beta is going to remain same, then you can get epsilon 2 star here. Okay. So just considering one element, how to get all the principal strains, then effective strain, principal stresses, alpha, beta of course, and then you have a sigma bar, then you can get a T1 and T2, and further if you put this particular condition, okay, for maximum tension you can get epsilon 1 star, that is the major strain, principal strain at which maximum tension is reached, okay, after which you will see a decay in T1, okay, and correspondingly T2. So which is actually different, that is n minus root 3 by 20 epsilon naught, because you are bringing in epsilon naught into this equation, okay. So now we are going to the next one. So we need to get a few more important quantities required during this deformation. What are they? So we need to get a P. P is nothing but contact pressure. P is nothing but contact pressure. Okay, we need to get that. So for this particular diagram A to D would be useful. Okay, and this is similar to your previous one. So let us say this is your punch, rigid punch, let us say, and this is your sheet, which is actually sliding on the punch surface and it is getting deformed, let us say. Okay, and this is an element of arc length, let us say ds, it is given here. Okay, so and length of the element, okay, ds is nothing but your d theta into r, where r is your your radius of curvature of this particular punch. So r into d theta will give you ds, okay, and force acting on the element radially is nothing but you have pr d theta, okay, this is pr d theta, right, r d theta, okay, and then pr d theta will be nothing but your force acting on radially, and here this p is actually called as contact pressure, okay, this is nothing but your contact pressure. And because of P, okay, there is going to be one mu P which is going to act towards left, because the sheet is actually stretching against it, okay, the sheet is actually stretching, sliding against it. So naturally mu P will be in the opposite way, and that will give you tangential force due to friction, which is nothing but mu P r d theta, mu P into r d theta, okay. These both the forces are actually plotted in this particular figure. You will see that this is the same element, okay, and P r d theta is acting in this normal to this, and mu P r d theta is in the tangential direction, and you will see that there will be some slight change in thickness from one location to another location, which we are going to term as T on one side and T plus delta T on the other side. There is some small change, okay, and because of that there will be some change in tension T1 and T1 plus DT1. So T1 is major tension, there will be some change in tension T1 plus DT1 along one direction. This is along one direction, no? So this is along one direction. This is 3 direction. Okay, so all are plotted here. So now what I am going to do is I am going to plot this particular graph, which is also easy to understand. So I am going to arrange all this tension in this way. So my T1 plus DT1, okay, is kept in this way, and then this is my d theta, so that this one will be T1 d theta. This one will be T1 d theta. Okay. So then what I am going to do is, now I am going to find out the equilibrium of forces in the radial direction, that is along this direction, okay, radial direction. So what I am going to do, T1 d theta would be equal to my PR d theta, which is what I am given here, and this will lead to P is equal to T1 by R. P is equal to T1 by R, okay, or this T1 can also be written as what is T1 for us here? We already discussed this. T1 is nothing but sigma 1 into T, sigma 1 into T, right. So sigma 1 into T, so sigma 1 divided by R by T, okay. This R by T is actually called as bend ratio. This is going to be important for us, which we will discuss in bending, okay. So we are saying that this contact pressure is inversely proportional to the bend ratio. Contact pressure is going to be inversely proportional to your bend ratio. That is the first one. So contact pressure, how do you get? If you know sigma 1, if you know R, and if you know the current thickness, then you can get P. How do you get sigma 1? Sigma 1 at that location can be obtained by one of the methods described here. Sigma 1 we already discussed. Sigma 1 divided sigma bar divided by square root of this one to sigma bar by square root of 3. Okay. So in that way you can get sigma 1. R is basically, it depends on the your punch dimension, okay, and then T is the new thickness, you know how to get it. So now if you want to take equilibrium along the sheet, then we can write T1 plus dt1 minus T1 would be equal to mu p r d theta. So T1 plus dt1 minus T1 will be equal to mu p r d theta. So direction you can check accordingly, and you will see that this PR, what is PR? PR is nothing but this PR, yes, PR is nothing but T1. You know? So PR is nothing but T1. Okay, so I can directly write dt1 by T1 is nothing but mu d theta. Okay, dt1 by this T1 PR is nothing but mu d theta. Okay, so what does that mean? That means the change in tension between these 2 points. Okay, these two elements, these 2 points, no, how much is a change in tension between these 2 points which are actually deforming and sliding below the the punch. Okay, that change in tension, okay, is independent of the curvature and is just a function of coefficient of friction, and we are going to call this d theta as angle of wrap. Okay. Okay. So here pressure actually depends on the bend ratio, okay, which also depends on the curvature, but the change in tension does not depend on the curvature, rather it depends only on coefficient of friction and angle of wrap. So now this equation not only is useful to relate change in tension with respect to some known parameters like mu, and mu is Coulomb's coefficient of friction, that you know. Okay. So you can substitute some values and theta is known, you can get this. So basically not only is going to give relationship for evaluating change in tension, okay, it is also going to give you how to calculate tension T1 if you know tension at another point. Okay, so that's what a small derivation is given here. If the tension at one point j in the section is known, then the tension at some other point, let us say, can be found by integrating this equation. If you integrate it, so you will get T1k, okay, will be T1j exponential mu into angle between those 2 points j and k. Okay. So where T1j, if you know, T1j has to be obtained from original equation, this one. If you know that, then you can get T1 another location if you know coefficient of friction and angle between these 2 points. Otherwise, in another location also you can get this way also, provided you know all these values. If you do not know, the best way is to use this particular relationship. But here you should know what is mu, what is the angle between these 2 points. Okay. So now this is what is going to happen between sheet and the punch. Okay. So now if you go ahead and then go to this particular location, okay, this particular location where blank holding is going to play a vital role in sheet deformation. So now the question is, how is the situation there? Situation there is actually can be written in this particular way. So force equilibrium at the blank holder and punch. Okay, force equilibrium at the blank holder and punch. So now region EF, okay, we are going to call this region as EF. Okay, you are going to call this region as EF. Which region is it? It is just below the punch. This region EF, on this region, okay, your B is going to act, right? So that region we are going to pick up and we are going to draw, this. Okay. So sheet is clamped between 2 flat surfaces and the force is expressed as directly I am going to write. So where B is my blank holding force acting from both the directions. Okay, and my material, if at all it's going to deform or slide in this way. So your mu B is going to act opposite to that to restrict that movement. And T1E is a T1 at E point. T1 at E point. E point is this particular point. Okay, D point is just at this particular point. Okay, so E is here. So this is your EF, no? EF, just outside that whatever tension is acting, that is your T1E. Okay, T1E. Okay, the T1E, if you know, then you can calculate blank holding force, okay, from this expression. So I am simply writing T1E is nothing but 2 times of mu B. 2 times of mu B. Okay, so if you see, generally between this E and F, wherever you are going to have this, where your blank holding force is going to act, B is going to act, generally it is sensible to keep that as a linear variation. That means at E, you will have T1E value, and it's going to decay linearly, okay, at F, and at F it's going to become 0. Okay. So what I am saying is, suppose you want to plot T1, okay, with respect to EF distance. Between E and F, I am going to plot T1, then it is sufficiently accurate to assume that this T1E is going to be, or T1 is going to be maximum at this E point and is going to linearly decay and become 0 at F. Okay. And this variation is a simple variation you can assume, but depending on your draw bead force, all those things, this variation can change. Okay. So the tension is actually reduced linearly in this fashion. Okay. So now I can get B from this. I can get blank holding force from this. It's a T1 E divided by 2 mu. So now I want to get punch force. Okay. Punch force is this F. Okay. Contact pressure has been obtained. So now I want to get this punch force F. Okay. And this punch force, there are a lot of ways to get it. And then you will see that very simple analysis we can do to get this F. For that, I am going to use this particular figure. This can be understood easily. So it is the O location of the sheet. Then you have A, B, C, D, E, F, G will come in from here to here. And my interest is between B and C, which is nothing but my cup wall region. Okay. So theta B can be obtained from the geometry of the deformation. Okay. Then what I am going to do is, so I am going to say that since this is a unsupported region, okay, then since in this unsupported region, so I am going to have T1B acting along this, T1B acting along this, okay, which is going to have an angle of theta B with respect to x-axis, so that my vertical component of this is nothing but T1B sin theta B, T1B sin theta B. Okay. So T1B is a tension acting at a point B along the cup wall or the side wall, okay, in this direction. So which is going to have theta B with horizontal axis, and which will give my vertical component as T1B sin theta B. And what I am going to do is I am going to equate this F and this and put 2 before, twice that of the tension T1B sin theta B, because it is taking as a symmetric with respect to the axis. Okay. So we can get the force per unit width considering both sides of the sheet. We can get it as F is equal to 2 into T1B sin theta B, where theta B has to be known to you, okay, and T1B has to be calculated with the previous expression that we have derived in general for T1. Okay. So now this all are calculated. I have written 1, 2, 3, 4, 5. You can imagine strain of an element, then you have thickness, then stress on that element, then you can say tension or traction force T1, T2. That will lead to this important expression for us. And then we have equilibrium of forces in 2 ways. One is radial direction and along the sheet. Both will give you 2 important outputs. One is contact pressure, other one is change in tension. If that is known, then you can get a blank holding force, okay, by this particular expression, and then you can get a punch force by this particular method. Okay. And here you will see that this T1, okay, here this T1 depends on several things, right. So T1 is actually depending on the material, its hardening ability, everything. So you can have material properties K and N coming into picture, T1, no. So K, N comes into picture, and original thickness of the sheet comes into picture, okay, and the pre-strain if you want, that will come into picture, and your how much amount of deformation you have given, that actually changes epsilon 1, okay, and hence T1. So, okay. So your punch force can be plotted, okay, F can be plotted with respect to change in strain, okay, F can be plotted with respect to change in strain, okay. So I am not going to show that, but if you want to calculate it, you can calculate it. So now just to give you some idea of how this tension distribution over this section is going to be, then this diagram would be useful. Okay. This is the same diagram. I have just taken only the sheet. Okay. The stamped component is from O, A, B, C, D, E, F, G. OA is below the punch face, and AB is that your punch corner radius, BC is a side wall, CD is die corner radius, DE is the unsupported land width region, EF is a location where blank holding was going to each, and FG is a free end. Okay, so now in this you will see that this is a point O. Okay, this is your point O here, and in this entire section I am drawing between T1 and a distance, T1 and distance you can say. Okay, let us call it as S, T1 and distance S. So you will see that at particular point O, you have some tension T1 which can be calculated from the previous equation, and at A there is some slight increase, and in the corner there will be significant increase, and BC there is a constant value, and CD is going to follow similar to what is given in between A and B, and is going to somehow reach almost same as that of this particular point. Then DE is going to remain almost same, and EF situation we already discussed, okay, where E is your T1E and suddenly decrease linearly to 0 at F, and FG is a free end, it will remain 0. Okay. So now there will be some slight increase in tension, okay, because we are going to choose a gently curved punch. Okay, the punch is not it's not curved significantly, it's gently curved punch, and tension is going to increase gradually between this point and this point. That's why I have shown the gradual increase, okay, between O and A. Okay, between O and A. Okay, so now AB is a corner, so naturally we expect the tension is going to increase significantly. Okay, tension will increase from O to B as the sheet is sliding outward against the opposing friction B to O. Okay, because your sheet is drawn stamped in this way, okay, you can expect okay, your tension to increase between in this corner region. Moreover, it's a corner region, we expect tension to be larger when compared to the other location. Now, what is the situation in B and C? B point and C point will have same tension because it's a side wall, it's unsupported region. Okay, it's to some extent sensible to keep it as a constant value. And if you move from C to D to E, okay, C to D to E is again, CD is nothing but the corner region, and you will see that it's going to decrease significantly, and this point, your D point and this O point, okay, your D and O point will remain almost same. Why? Because it is the same angle. Yeah, it's the same angle at which you are actually crossing. Okay, the same angle. Okay, theta B and theta is going to be crossed here also. So assuming that, then we can say that you can say from C to D it's going to decrease, and from D to E it is going to remain constant because it is again unsupported region, and from E to F there will be linear decrease in your tension as per this particular our discussion. E to F, E to F it's going to decrease linearly, and FG it's going to become 0. Okay, so we have to be a little bit careful. That is why in this punch corner region where there is a sudden change in your tension, where there is basically sudden change in your tension. Okay, there is a slight increase because it is a gently curved one. This is a corner, so naturally tension will increase. This is a side wall region, so tension can be made as same between B and C. Okay, and then since it is again a corner, it will slightly decrease. Okay, and your D and E will have lesser tension as compared to the other locations, and naturally it is also sensible to see tension decreasing up to this point, and EF is actually linear decay, and after that it is going to remain 0. This is how tension is going to change. And if you want to see how strain and thickness distribution is going to change in this cross section, okay, these are all some values given from this particular book, you can look into it. Okay, so again it is referred with respect to O, A, B, C, D, E, okay, up to that. And you will see that thickness has got one particular value from O to A, okay, they say it's almost same thickness, and then at the corner region is expected that it is going to decrease, okay, and because the tension is going to remain same between B and C, thickness is going to remain same, okay, and at D and E, between D and E, since it is a unsupported region, it will not thin down like what it was in this region, so naturally it will increase, okay, and then you can connect this to this with an increase in thickness, and then it will reach E. Suppose if you want to take strain, strain is generally opposite in nature, you can see there will be some strain value between O and A, okay, and wherever thickness is coming down, you see that strain is going to be significantly larger, and here it is going to be constant, strain is going to come down, okay. Why? Because between D and E there will be decay in strain, okay, and this fellow will come and join here, so to get DE profile. Okay, so again you need to be a little bit careful in this transition zone between A, B, C, D. Okay, A, B, C, D, where your both the corners as well as your side wall region is going to come. Okay, this is where your thickness and strain are going to change. Probably some values are given here for you to note down. And you will see that, so this accuracy of this simple model, okay, depends on certain assumptions. Okay, so now here we have not considered what will happen if sheet, because of sheet bending and unbending, right? Sheet actually bends and unbends at a few different locations. We are not going to consider that, and because of that bending there will be strain hardening in the material, that also we have not considered. Okay, so bending and unbending under tension, with tension, no, because it is stretching. Okay, reduce the sheet thickness, which will cause an early failure in the side wall. That is why I am saying the side wall is important. Okay, see the side wall, this location, no, this location is going to be very important, because you see that thickness is going to decrease drastically in this location. You will see strains are going to be larger. So we have to be a little bit careful, and it will cause early failure in the side wall. Okay, because of this bending and unbending. Okay, under tension. Okay, it is just not your moment, it is moment with tension that is actually happening here. So that's why you say bending, unbending under tension. Okay, so that's going to reduce the sheet thickness, because of which you can expect a thinning, more thinning, and hence there will be fracture in the side wall. So you have to be careful in these locations between this corner, no, your die corner, punch corner, and in between that in the cup wall. You have to be a little bit careful. Okay, so now this brief calculations can be done if there is any stamped component. Okay, some typical schematic is given here. You can see that, of course, this is your you can say your die, and this is your black color line is your sheet or blank. Okay, and you will see that some dimensions are given here. Okay, so these 2 points called as D. Okay, so distance between that is actually 2D naught. Okay, so 2 points we are taking on the two extreme locations here, and then between the sheet edges you can call it as 2B naught, and the new position of this after some deformation is actually, you will see that it is D dash to D dash, which is nothing but 2D. So 2D naught, it has become 2D, and 2B naught has become 2B. So now if that is the case, you can evaluate stretch ratio or stretching ratio and drawing ratio like this. So stretching ratio SR is given by your D minus D naught divided by D naught into 100%, and drawing ratio is given by your B, that is a new your width, minus B naught divided by initial value into 100. So this will give you stretching ratio and drawing ratio, which will be useful for some calculation. So how much of stretching ratio has been obtained when you stamp a component, how much drawing ratio is obtained, you can get it from this. This drawing ratio would be useful, or draw ratio would be useful in deep drawing also. Okay, we will see that later on. In deep drawing also we will see this terms. Okay, so before we complete this particular module, okay, which is a small one, let us do 1 or 2 problems in this. We will give an idea of what is going on. So the first question is, okay, so a material is deformed in plane strain, that is already given here, with a major tension of T1 is given here, 340 kilonewton per meter. The initial thickness of the sheet is, let us say, 0.8 mm, and the material is going to follow the strain hardening law. Sigma bar is equal to 700 epsilon bar power 0.22, and K is given in MPa. Okay, so you need to get major strain epsilon 1 at that particular point, or at that particular element, you can say. So straight away what we can say is, for plane strain, which we have discussed already, we derived a relationship between T1 and epsilon 1. We already have that relationship is given here, and since this is sigma bar is equal to K epsilon bar power n, so epsilon naught is actually, pre-strain is actually 0 here. So you will get this particular simple equation, T1 is equal to 2K T naught by square root of 3, the same equation which we discussed before, this equation, this one, same only, 2K T naught by square root of 3, this fellow will become 0 plus 2 by square root of 3 into epsilon 1 power n, because this comes because of plane strain, exponential minus epsilon 1. So same equation is actually used here. So now what is the question? T1 is given, K is given, T naught is given, n is given. So that's all. So substituting all these values, you have to iteratively solve this, for which value of epsilon 1 you will get this T1. Okay. Or other words, what you can do is like you can change all these components on terms on one side and keep only epsilon on other side, you can get this expression. So 2 by square root of 3 epsilon 1 power n exponential minus epsilon 1 is kept here. Okay. So T1 into square root of 3 divided by 2 k T naught is kept here. You can substitute all these values. So T1 is 340 into 10 power 3. Square root remains. K is 700 into 10 power 6 because 700 is a megapascal, and T naught is 0.8 10 power minus 3. So all are consistent unit you can keep. Okay, and then you can solve this to get 0.526. So now you need to check for which value of epsilon 1 you get 0.526. You can take a small value and start evaluating it. So if you put epsilon 1 as 0.08, you get 0.547, then 0. This one, then 0.06, you get 0.523 approximately, which is same as it of this. So epsilon 1 would be equal to 0.06 is a way you can get epsilon 1. Okay. So at that particular point, you will get a major strain of 0.06 when you give a tension of T1 as 340 kilonewton per meter, and it has got initial thickness of 0.8 with this particular strain hardening law. So that is what you will get. So now let us go to the next question, okay, which is a little bit complex. Okay, let us discuss this one by one. So this is a two-dimensional stamping process which is provided to you. It is the same diagram like what we discussed before. We had only one section of this, one part of this, one half of this. Okay, now it is full part is given. Okay, blank holding force is acted. Okay, so everything is given to you. So this is your punch, black color line is the sheet. So it is said that situation is given as side walls are vertical and face of the punch is flat, everything is given. If the blank holding force B is increased, okay, if you slightly increase the blank holding force, that is the situation. They are asking determine the maximum strain that can be achieved at the central line. That means this particular, they are calling it as epsilon 1 max. Okay, they are going to call that as epsilon 1 max at the center region. Okay, when B is increased. When you increase B slightly, the strain epsilon 1 reaches its maximum. That is the situation. When you increase blank holding force little bit, okay, here what you will see that epsilon 1 value is going to be maximum. And then coefficient of friction is 0.15 is given, and the stress strain law is given as sigma bar is equal to 600 epsilon bar power 0.12. K and N are given in MPa. Now they are also asking maximum strain as well as what is the blank holding force required to reach this if the initial sheet thickness is 0.8. Okay, the same sheet which you have used before. Okay, so if you use the same thickness 0.8 mm, okay, so what is the blank holder force that is required to reach this particular strain which you are going to calculate, so that you give appropriate blank holding force such that strain here will be lesser than this strain, because maximum strain means there is something is going to happen there after that. So that is the situation. So what we are going to do is we are going to put this condition which we already derived before. Okay, so we are going to say that when you slightly increase the blank holding force here, okay, the wall tension is going to reach maximum, and because of that this epsilon 1 here will reach its maximum, and wall tension will reach its maximum means you can put a condition maximum wall tension is when epsilon 1 is equal to n. Why epsilon 1 is equal to n? Epsilon 1 is equal to n is a condition which we got before here. Okay, we say epsilon 1 star is nothing but root 3 n minus root 3 by 2 into epsilon naught, no. So epsilon naught is anyway not there, epsilon 1 is equal to n. So what is the condition we are going to keep here is when wall tension is going to be maximum, epsilon 1 will also become maximum, and that can happen because of any slight change in blank holding force, and when it becomes maximum epsilon 1 will be equal to n. Okay, so T1 is going to become T1 max. The conventional T1 which we have used in the previous equation, say for this equation, the previous problem, this is going to become T1 max. Why? Because this epsilon 1 is going to become n, equal to n. That is what we have written here as T1 max is equal to 2k T naught by square root of 3 into 2 by square root of 3 into n power n exponential minus n. In place of epsilon 1 we are keeping n. Okay. So now what we are going to do is, so this T1 at the center point is given by T1 max is at any location. We have not specified anything. T1 max divided by exponential mu into pi by 2. This also we derived. Okay, if you want to know tension at one particular location, you can multiply that with exponential mu into pi by 2, which will give you T1 max divided by exponential mu into pi by 2. Mu is this. Okay, T1 max divided by exponential of 0.15 into pi by 2, and this T1 naught is going to be equal to T1b. Somehow we have to bring in blank holding force into picture. Why? Because we need to calculate this, and for that we are going to use this particular situation. That situation is this situation, like this. Your T1 at this location will be same as that of what you got here. What you got here. Okay. At this particular, so basically this particular point is what we need, because this is where your blank holding force is going to act, no, between E and F. So this particular point you need. This is same as that of this particular one. So we are going to pick up this particular relationship, saying that T1 naught is nothing but T1 max divided by exponential 0.15 into pi by 2. That will be equal to your T1b, but T1b is a general case. But T1b is actually a general case. Epsilon 1 is not equal to n there. T1b is a general case. So you will keep this original form of the equation as it is. That's what we are going to do. Okay, you see that. So now T1 max is this 2k T naught. Okay, so I am going to substitute this here. Okay, so 2k T naught divided by exponential 0.15 into pi by 2 would be close to 1.266 into square root of 3. This will remain same, 2 by square root of 3 into what is n? N is 0.2 power 0.2 exponential minus 0.2. So this entire thing has been written in this way. This fellow will be equal to a general case T1b. That will remain same as our original equation, is nothing but 2k T naught by square root of 3, 2 by square root of epsilon 1 power 0.2 exponential minus epsilon 1. Okay. So all the values are known to us, okay, except your epsilon 1, and you can modify this equation in this way. So all known values you can take it on right hand side, all unknown values you can keep, which is nothing but epsilon 1, you can keep it on left hand side. You can arrange this, you can do some small calculation in between, and like in the previous problem, you iteratively solve this by giving different epsilon 1 values. Okay, and finally you will see that for this particular case 0.002 epsilon 1 if you keep, okay, your this right hand side value is going to be same as that of 0.469. So epsilon 1 will be equal to 0.026, okay, to get this particular situation. Okay, so that's a question, no, determine the maximum strain that can be achieved at the center line. Okay, so you have to have this much amount of strain at the center line. Now for this, how much is a blank holding force? That's the next question. So what I am going to do now, I am going to now epsilon 1, I am going to put it here. Okay, so 2 into all the k values, k value you can give, the thickness you can give divided by 1.26 into root 3. Okay, and I am put 0.026 here, 0.026 here, and I am going to get my T1 naught, which is be equal to T1b, which is nothing but 267 kilonewton. Okay, this one. If this is known to me, then I can get a blank holding force. How? 267 divided by mu b. This equation, no? 267 divided by 2 mu will give me b. Okay, that b is nothing but my blank holding force. Okay, which is what I am getting as 890 Newton here. You can check it. The calculation is correct. Okay, so this way one can solve this particular problem. Okay, so this little bit of, you need a little bit understand this. So we are going to put this condition to get maximum strain at the center location. Okay, so same situation does not exist below blank holder, so you are keeping a general form of the equation. So by equating these two, okay, you can get strain, okay, and then you put the strain value, okay, to get your T1O or T1B, okay, both are going to same, and then that can be used to get your blank holding force. Okay, so we stop here with this particular section, and then the next session we can start a new module. Thank you.